In the last video lecture, we discussed logical dependence, and we studied the square of opposition in order to know whether or not if one proposition is true, is another proposition in the standard four categorical propositions also true? Or if one of the standard four categorical propositions is false, is another one also false? Or is its truth value undetermined? Or if it's true? Today we're going to start to study logical equivalence, and in order to understand logical equivalence, we're going to have to distinguish it from a few other related logical relationships. Now, when we study logical equivalence, one thing we have to distinguish it from is what we call logical consistency, or two propositions that can be logically consistent. Now, we've already looked at logical consistency. I don't know if we called it that in the previous lecture, but two propositions are logically consistent just in case it is possible that they are true at the same time. Now, propositions that are logically consistent, they don't necessarily mean the same thing, and they're not true under all the same set of circumstances, but to be logically consistent, it just means that they can be true under some set of circumstances. So, for instance, take these two propositions, John died and John is alive. Is it possible that these two are true at the same time? And the answer to that is yes. It is possible that they are true at the same time. How? Well, maybe John died and then he was resuscitated. Maybe he flatlined on the operating table and then he was resuscitated and now he's alive and let's say he's doing fine. Good for John. Well, in this case, it would be true that John died, but it would also be true that he is now alive. So these, even though they clearly don't mean the same, they are logically consistent for the simple reason that under some assignment of truth values, it is possible for these two propositions to be true at the same time. Or take the following two propositions. All S are P and some S are P. Now, quite clearly, these don't mean the same thing, and they're not true under all set of circumstances, but there is at least one, probably more than one, but there's at least one set of circumstances under which these would be true at the same time. And since it is possible for these two statements to be true at least sometime, let me rephrase that, it's possible for them to be true together at the same time, then these statements would be logically consistent. Now, we can contrast logical consistency with logical inconsistency. And two propositions are logically inconsistent just in case it is not possible for them to be true at the same time. We studied this last class when we looked at the square of opposition. But here's an example. John is dead and John is alive. It is just not possible for these two statements to be true at the same time. Now, you might say, well, he's dead spiritually but alive physically. Okay, well, now you're changing the propositions that are being asserted here. But assuming that these two statements express one of them means dead bodily and the other one means alive bodily. So we're not changing the meanings of what these appear to express. Then these statements are just not logically consistent. They cannot be true at the same time. Or here's another example. All S are P and no S, I should have said, is P. I told you a while ago that I probably type this incorrectly from time to time, but no S is P. In any event, all S are P and no S is P. These cannot be true at the same time. So these two statements here would be logically inconsistent. Now, we had talked about both logical consistency and we had talked about logical inconsistency in the previous discussion when we talked about the square of opposition. Like I said, I don't recall using these terms, but that's basically what we were studying. Now we have to distinguish what's going to be the subject of today, which is logical equivalence. And two propositions are logically equivalent just in case they have the exact same truth conditions. That is to say, they are true in all the same circumstances. So if one of them is true, the other one's going to be true at all times. Let me give you a few examples. John is dead, John is not alive. Here's an example. These two statements, you might say it this way, they mean the same thing, but basically if the first statement is true, the second one's going to be true. If the first statement is false, the second statement is going to be false, and vice versa. These you could say it, they mean the same thing, but we're talking about it in terms of truth conditions, but they have the exact same truth conditions. If one's true, the other's true. If one's false, the other's false. Or here's another one. I don't know why I'm picking on John so much, but John bought apples and bananas. John bought bananas and apples. Notice the only difference here is I switched the order of apples and bananas. But these two propositions here, they're going to be true in all the same set of circumstances. There's not going to be a case where you say, well, he bought apples and bananas, but he actually didn't buy bananas and apples. No, they would always be true at the same time. And then finally, this one's a little complicated, but pay attention. The chance you will die one day, all of these examples, so many involving death. Sorry, I'm not feeling morbid today, but the chance you will die one day is greater than 0. So there's a greater than 0 chance you will die one day. And there is a non-zero probability that you will die one day. Well, if it's non-zero, that means it implies that it's greater than 0 because, probability goes from 0 to 100. So if it's non-zero, that means it's going to be 1 to 100. So these two statements express the same thing. If one's true, the other's true. If one's false, the other's false. Now I want to make a quick point here, because if two statements are logically equivalent, then that means that they are also logically consistent. So two statements that are logically equivalent, like John is dead and John is not alive, well, these mean the same thing. So that means that there is some possibility in which they're both true at the same time. In fact, they're true at all the same times. So if two statements are logically equivalent, that means that they are also logically consistent. But the opposite way doesn't work. Just because two statements are logically consistent doesn't mean they're equivalent. Just as up here, all S are P and some S are P, these are consistent but not equivalent. These down here are consistent and equivalent. In fact, they're consistent because they're equivalent. So these are going to be three important relationships between propositions that we need to understand as we move forward. Today we're going to focus very heavily on equivalence. And we're going to be focusing on equivalence with respect to the 4 standard categorical propositions. And each of these can be rewritten to express a logical equivalent. Now you might be wondering, why in the world will we bother with doing this, rewriting these to express a logical equivalent? Well, because as it turns out, we often speak in ways just ordinarily in which we say something and it is equivalent, though it's worded differently than the 4 standard categorical propositions. And I'll give you some examples and maybe this will make a little more sense. But look at these two statements. All non-employees must leave, and no non-employees can stay. Look at that for a second. All non-employees must leave, no non-employees can stay. These two statements are logically equivalent, but they're not worded the exact same way. In fact, the quantifier in this right here is different than the quantifier here. And must leave and can stay. Basically these are the opposite of one another. So what we've done is we've changed the quantifier, and then we've also changed the predicate here as well. We've negated both the quantifier and the predicate in order to derive a complementary but logically, I shouldn't say complementary, in order to derive a logically equivalent expression. Here's another one. Some pirates are criminals, some criminals are pirates. Yet again, these two statements, they're said differently, but they're logically equivalent. They're going to be true in the exact same set of circumstances. If this statement is true, this one's true. If this one's true, that one's true. If this one's false, that one's false. These are logically equivalent. Another one, all whales are mammals, no non-mammals are non-whales. Now, this one's a little bit tricky here. You might not be able to understand it and fully figure it out. And we do sometimes speak this way. A lot of times when we might say something the way I've expressed it right here, all whales are mammals. And sometimes we'll actually say things like this, though we won't use a lot of times the words like non-mammals. Quite often we'll have English words that express what is called a complement of a term. A complement is, I'm getting a little bit ahead of myself, but like non-mammals is the complement of whales. Basically, this term right here excludes everything from the class of whales. Not whales the country, but whales the animals. And we have complement terms in English, and we use these sometimes, and the reason it's important is because when we're making an argument, ordinarily we'll use these class complement terms, and it can be confusing understanding what someone has said because what you said is structurally, grammatically different, but is actually the exact same thing. So we have to be able to figure out, okay, well, what you said, it sounds different. Oh, but wait, you're saying the same thing, you're just using different words. Now, when it comes to figuring out equivalence between categorical propositions, as I said, it can be a bit tricky. And looking at something like this, it just might not be intuitive to you. And we have a tool that we use in order to determine whether or not two propositions, categorical propositions, express, or I shouldn't say express the same thing, but are logically equivalent. And this is the method of using Venn diagrams. Now, some of you might be familiar with Venn diagrams from your math class, but we're going to be using Venn diagrams. I've heard students say, well, this is done a little bit differently in a math class. So if you've done them in math class, just note that what we're going to be doing here is just a little bit different than some of what you've done in the past. But basically the method of Venn diagram, it involves overlapping circles, and then it's going to involve two, I don't know what you want to call them, two tools or notations that we use. One of those is going to be we shade an area of the circle, and another is going to be we use an X in the circle. And basically the shade means that nothing exists in this area, whereas the X, and this is a little maybe backwards what you're thinking, it actually implies that something does exist in that area. Now, this is all very confusing at this point, not particularly concrete. So I'm going to begin to show you how this works. Now, all right, so as I was saying, the way that we do Venn diagrams is that they consist of basically at least two overlapping regions or circles. And you're going to have to excuse my drawing here. I'm not the best artiste ever. But we have one circle, and then we have another circle. And each of these circles, they represent classes of things. So we're just going to use the letter S here to represent this class called P, this class called S, and then another one to represent P. And notice that we have three regions. We have region 1, we have region 2, and we have region 3. That's poorly written, but hopefully you can see regions 1, 2, and 3. And then S, this is equal to, hopefully you can see region 1 and region 2, while P is equal to region 2 and region 3. Now, what we use Venn diagrams for is, like I said, we can represent 4 standard categorical propositions with them. And we're going to use two notations in order to demonstrate how propositions relate to one another. Shade is going to equal empty. So when you see the shade, just think, hey, there's nothing there in the area. That's hopefully you get that shade right there. That's not letters. Just whenever you see shading, just think empty. Whereas X, this means exists. So how does this work? How can we symbolize or diagram our categorical propositions? Well, let's take one. And let's say some S R P. Now, how do you think that we might show that some S are P? Well, let's look at what we're saying here. We're saying that some members of S belong to the class of P. And so what we can do here is we look at, well, the areas. You can look right here. You can look at the numbers. It's going to be helpful in the long term to look at the numbers in the top right. But S is 1 and 2, and P is 2 and 3. That means that some members of S overlap in the region of 2. Some exist in the area of 2. So in order to show some S or P, basically we just put an X right here. And that shows us some X are P. Some S are P. I think it's some X. Sorry, some S are P. That one seems to be a fairly straightforward way, a straightforward diagram, but let's look at another one. Suppose we said some S are not P. How do you think we would show this? Well, the way we would show this is we'd say basically that there are some S that exist and they're not in the region of overlap between S and P. Now, we don't need to say anything about region 3 over here because it's not possible, even logically speaking, for S to exist in region 3. Why is it not possible for S to exist in this region right here, region 3? Well, because S, by definition, is 1 and 2. So we never, if we're saying some S are P or all S are P or whatever, we never need to say anything about region 3 because region 3 is just beyond the purview of S. S is always going to be limited to 1 and 2. So if we're saying some S are not P, that means that some S exist in the region where 1 and 2 don't intersect. They intersect at 2, they don't intersect at 1, so we'd put an X right here. This is how we'd say some S are not P. Okay? Hopefully that makes some sense. Now, let's erase this. Finally, we come to, oh, not finally, sorry, now we come to no S are P. And in order to say this, basically you have to think about what we're saying. We're saying nothing exists where S and P intersect. They intersect in region 2. So you're saying nothing in the world exists or is possible to exist in this area. And like I said, we use shading here to show that stuff is empty. So what we do is we'd shade in this whole area. We shade this region in. And if you want, you can get complete with it. It's not necessary. I think that demonstrates the point here. But this shows that nothing exists in this area. Nothing exists in the region of intersection here between S and P. All right. Now, we actually come to the most difficult and least intuitive. I honestly believe that those three are not hard to see. That when you see them spelled out, it's kind of straightforward. You just have to keep in mind that shade means empty. You know, like throwing shade at somebody, right? You're saying there's nothing there, right? You're disrespecting them in some way or another. So sorry, I was trying to erase over here. X means exist, just like the X in the word exist. Empty, we use shade. Now we come to the most difficult one to show, which is all S are P. All right, now in order to show this, you have to keep in mind what you're saying. And you have to keep in mind we only have two symbols we can use. We can use X and we can use shade. Those are the only two symbols we can use. And you're saying that all S, every S that exists in the world exists in this region right here, region 2. They exist in the area of overlap. And if we know that all the S exist in 2, then the question becomes, where do no S exist? And one place that no S exists is no S exists in region 3. But as I was saying a moment ago, we don't need to say anything about that or draw any symbols to illustrate that nothing exists in 3 because it's not even possible logically for something to exist in 3. Because again, S by definition is 1 and 2. So we only need to symbolize something about regions 1 or 2 in this particular case because that's the only place possible for any S to be. And we know that all the S that exists in the world are in 2 because all S are P. So they all exist in the region of overlap, which means they exist. Where don't they exist? If they're all in 2, that means none are in 1. And how do we show that an area is empty, that there's non-existence there? We shade it in. We shade it in. And so this is how we would symbolize all S are P. We'd symbolize it by shading in the region entirely. And this shows us here, if you look at this you have to think about what this is saying. This is saying that no S are in 1, and all the S that exist, they're going to be limited to region 2. They're going to be limited to region 2. And this shows us that all S are P. And this is basically how we do Venn diagrams. And I know the million-dollar question some of you are asking right now, I always get asked this by students, which is why? Why do any of this? This seems so absurd and preposterous. The answer goes back to what we were talking about earlier with regard to logical equivalence. And remember, I said that when it comes to the categorical propositions, we can show that they are logically equivalent one with the other. And we're going to be looking at one way of showing whether or not propositions are logically equivalent, or one, I should say, type of relationship that exists between propositions. And we can show that the propositions are either logically equivalent or that they're not logically equivalent through the use of Venn diagrams. So we're going to begin with one logical relationship that exists between propositions, and that is called the converse, or what we call conversion. The converse relation or conversion. Man, that looks terrible. I'm sorry. Look, this is not as easy as it looks, or maybe it's as difficult as I'm making it look. I'm writing on an iPad with a stylus, and it's just, I don't have good handwriting anyway, not to make excuses, but you don't care. This isn't therapy. So in any event, what a converse of a proposition is basically when you swap the predicate term with the subject term. So if you were to take a statement like the following: all S are P. Its converse would be switching the subject and predicate. So the converse of all S or P is going to be all P are S. And we have a question here. Is the converse of an A-form proposition right here, are these logically equivalent? Is all S or P logically equivalent to all P are S? Well, we're going to come back to that in a second when we've had a little more practice doing some Venn diagrams, because this one is a little bit tricky. So we'll come back to that in just a moment. But let's do one that's going to be a little easier to do. And we're going to come back to that one because, like I said, that one's a little bit tricky. And let's look at this one. Some S are P and some P are S. Are these two statements logically equivalent? I'm sorry, equivalent. Yeah. Are these two statements logically equivalent? Notice that I'm going to just write 1 here and 2 here so we can keep these straight. That 2 is the converse of 1 and 1 is the converse of 2 because we've just swapped the predicate term with the subject term. Well, we can Venn diagram these in order to determine whether or not they are logically equivalent. And here's how we do that. We draw up our Venn diagrams just as before. Those circles are kind of small, so let's see. All right. So let's see here. Sorry. This thing is giving me a fit. All right. There we go. Good enough. We have S and P. We have our 3 regions like before. And you might recall, how do we diagram sentence 1 up here? Well, we just put an X right here. And that shows us that some S or P. Well, how do you think we would diagram some P or S? Now, we have to keep these in the same order. If we switch P and S, like I put a P on this side and an S on this side, that wouldn't work. So we keep P and S in the same places they were. How do you think you'd show that some P are S? Well, basically, you just put an X right there. And that shows you that some P are S. And so we look at these and we say, well, look, this diagram here is the exact same as this diagram here. So yes, and for an I-form proposition, its converse I-form proposition, its converse is logically equivalent. And some of you may have known this already because you could just probably look at these and tell this is pretty easy one. But we can use Venn diagrams here in order to prove that the converse is in fact logically equivalent. All right. Well, let's do another example. Why is this not working? Whatever. We'll just have to be slow about it. All right, so we know that an I-form proposition, its converse is in fact logically equivalent. Well, what about, let's say, an E-form? No S is P. This is going to be our first proposition. And then our second one, in order to form, good gravy, in order to form its converse, we'd say no P is S. Are these going to be logically equivalent? And what we do is we do like before, we draw our Venn diagram, S, and P. We number our regions. You might wonder why we're numbering the regions, why that's so important. Actually, we're going to get to some really complex diagrams later on, and that's going to become extremely important. So how do we diagram sentence number one? No S is P. Well, basically you're saying nothing exists in the area where they overlap. So we just shade in region 2. And then we come over here. We want to diagram the second one. No P is S. Again, just like before. 1, 2, 3. And we say no P is S. Well, what are we saying here? We say no P is S. We're saying that nothing exists where these two intersect. So we're saying this right here. And so when it comes to an E-form proposition, E-form, the answer is yes. We say that the converse of an E-form proposition is logically equivalent. So again, this is something, just looking at these, I don't know, maybe you could just obviously see it and intuit that these are equivalent. But by drawing the Venn diagrams, we can prove without any doubt that these two are equivalent because the diagrams are the exact same. All right, now we're going to do a slightly more complicated one. Suppose we want to do an O-form proposition. Some S is not P. So we're going to do an O-form proposition. We're going to say some S are not P. Well, how do we show the converse? Or what is the converse of this? Well, the converse is going to be some P are not S. Because remember, the converse, we just switched the subject and predicate. Plain and simple. All right, well, in order to figure this out, we come down here, we draw our Venn diagram just as before. 1, 2, 3. Put our S and P at the top so we can keep our this class of things straight from this class. And then some S are not P. Well, you might recall a second ago I said we just put an X right here, and that shows that some S are not in P. Well, how do we do this one? The second one. This one's a little, good gravy, Jesse. This one's a little trickier. 1, 2, 3, because you have to think backwards. But if you're saying some P are not S, what region is P? It is 2 and 3, and S is 1 and 2. So what you're doing here is you're focused on this. You're always focused on what's in the subject term. Whatever comes in the subject, the first part of the sentence right here, before the copula and after the quantifier, whatever comes there, those are going to be the only two regions that you will shade or you will put an X in. I should have said this earlier, and it slipped my mind, and this was really important. Whenever you're working with particular categorical propositions, so some or some not, you'll always use an X. You never use shade. You only use shade when you're dealing with all or no. And you never use an X when you're dealing with all or no. X is for some. So And in other words, I should have said this and I should have pointed this out earlier and it slipped my mind. But whenever you see the word some or some not, it's always X, right? And whenever you have all or no, it's always shade. So that's something to keep in mind as well. You never use shade for some or some not. You never use X for all or no. That's just, maybe that'll help you keep things straight. But let's focus on this again. So you're only going to put an X and what the numbers are in the subject term. So you can only put an X in region 2 or 3. And again, you're doing that because basically your quantifier is telling you that some P are not in S, right? Some P are not in S. So what we do here is we look at where these two overlap. And you're saying that some P exists in the region where they don't overlap. So some P are not in 2. And if some P are not in 2, where do we know that some P are? Well, you couldn't put an X in 1. Why couldn't you put an X in 1? Well, for the reason I just told you. You're only ever going to put an X in what is in the subject term. You wouldn't put an X in 1 because by definition, no P's can be in 1. P is limited to 2 and 3. So the only place you could put an X, all right, so look, if I didn't know anything that was coming after P, if I didn't know R not S, if that didn't appear, so let's just say you put your hand over that and block that out, you could only possibly put something in either 2 or 3 because that by definition is what P is. And if I know that some P are not a part of S, that means some P are not in 2, that means the only place they could possibly be is right, come on, there we go, computer, right there. So that's how we would show that some P are not S. And the question is, are these logically equivalent? And the answer to that is pretty straightforwardly no, because these two diagrams just don't look the same. So when we're looking at an O-form proposition, no, now I'm using X to mean no, not using X to mean exists. These are not logically equivalent propositions. All right. Why won't this? I guess I am on the biggest eraser that it has. Okay. I assumed that there would be one that was a lot bigger, but I guess that is not the case. Okay. Now we come to the most difficult one, the one I started with and said we come back to. This one is easily the most challenging. That doesn't necessarily mean it's, ridiculously hard, but what is the converse of all S or P? Well, in order to get the converse, you swap the subject and the predicate terms. So all P are S. Let me erase this little bit right here because that might confuse you. Kind of blurs in with the sentence below it. You swap those in order to get your converse statement. Are these logically equivalent? Well, in order to figure this out, we can draw our Venn diagrams. I swear I'm not having a brain aneurysm right now. 1, 2, 3, S and P. All right, and so hopefully you recall how we showed this a moment ago. But if you're saying all S are P, remember, S is equal to region 1 and 2. So if you're saying all S are P, students always have a hard time with this, and I understand why. It's because you have to think backwards on this. But once you get it, it'll make sense. So keep in mind, you're only going to put shade, and if you didn't know any of this if you didn't know any of this right here, the RP part, any of that, let's say all someone said was all S, you could only shade in one or two. Now you know you're going to be shading because you have all. Remember, whenever you see all or no, think shade. If you see some not, think X. But you're only going to be shading in region 1 or 2 here. And you're told that all S are P. Well, what you do is you look at the region where they overlap. And they overlap in 2. So if all S are a part of P, where would they not exist? Well, they don't exist in 3, but like I said, we don't care about 3 because S by definition is 1 or 2. So we're not going to worry about 3. We don't have to shade that in because it would be pointless to shade in and say, hey, they don't exist in some place they can't possibly exist. It's like, I don't know, I'm trying to think of something like saying, I don't know, there are no fish on the sun. Well, of course there aren't. They can't possibly be there. Or there, I don't know, no numbers or no numbers smell good or something. It's like there's no point of saying that because numbers don't have a smell. I don't know. These weird thoughts. Maybe you guys think I'm off my meds. Not that I'm having a brain aneurysm, but we don't need to worry about 3 because S is limited to regions 1 or 2. And what this statement tells us is it goes let me back up a second. If all I had was S, I didn't even have the R and the all, I would know immediately the only thing I would have to talk about, or only areas I could talk about, are 1 and 2 because that's what S is by definition. But the all and the RP, it's going to basically limit my knowledge or limit things to one of the to either of these regions. I'm going to be shading in either one of those. That's what the all tells me, is you're going to be shading in one of these two. When it says RP, that means that all the S that exist are in 2, and if all of them that exist are in 2, that means none of them are in 1. And this is what this shows me, is that no S basically is in 1 because all the S that exist in the world are located in 2. Now, I feel like, I know I'm probably beating a dead horse here. Hopefully none of you are upset that I used an example of dead horses and beating a dead horse, but hopefully I'm not beating a dead horse here with this one. But of doing the basic Venn diagrams of the 4 categorical propositions, it's always the A form proposition which students struggle the most with. But we just did one of this one right here, so let's see if we can do all P or S. And again, I'm going to draw our Venn diagram just as before with our 3 regions, S and P. And we're going to say all P are S. Now, when we do this, keep in mind, P is regions, run out of room here. P is going to be regions 2 and 3, and S is going to be 1 and 2. Now, just as I've said, we're only going to be we're going to be shading in either region 2 or we're going to be shading in region 3. So we look at the area where they overlap, and they overlap in 2. We don't care about 1 because no P could possibly exist in 1 because, look, P is just in this area right here, right? There's no P in 1, but we don't care about 1. It just doesn't matter to us. We only care about 2 or 3. And what this sentence is telling us is that all the P's that exist in the world are going to be in 2. And if all the P's exist in the world, where are they not? Like I said, we know they're not in 1 because by definition they're not. But where else are they not? They're not in 3. And what we do to show that all P are S is we shade in this area right here. And by shading this in, this tells us that every P that exists is going to be limited to the region of 2. And so we ask, is the converse of an A form proposition logically equivalent? And the answer to that is no. A converse of an A form proposition is not logically equivalent. So I do have some slides here, and you can look through those if they help you. The slides are basically just everything I just said, except I drew out I hand drew out everything for you right then and didn't post it on a PowerPoint. But here's just exact what I was just saying, and it lays it out for us. We take our standard proposition, the converse of an A form, no, it's not logically equivalent. E and I, yes, and then an O form, no. Now, for your homework, you're going to have a fair amount, I suppose, but actually it's not that bad, but you do have to do Venn diagrams for some of them. For these problems right here, the second set on 162, you basically have to look at Venn diagrams and determine whether or not they express propositions that are consistent or inconsistent. And that goes back to some of the stuff I was saying at the beginning of the video lecture today. But for the remaining problems, you're going to have to, for this first set right here, you're going to have to basically put propositions into standard form and then draw Venn diagrams. And then for these propositions down here, exercises on page 166, you're going to have to determine whether or not the converse of various propositions are logically equivalent. So if you have any questions about this, please feel free to email me and ask me. I know some of this is a little tricky with doing the diagrams, but I think the more you do it, the more proficient you'll become at it.